Looking at this last problem, we have find the radius of convergence for the power series of the summation from n equals 1 to infinity of -1 to the n times x to the n plus 1, all divided by n squared. What is our interval of convergence? So this time we want to find an interval of convergence, which means we are going to be ending with either the center only, or we're going to be doing two numbers and deciding what's happening at the ends. So first thing we need to do is the ratio test for our series. So we have the limit as n approaches infinity. Of the absolute value of. So in the denominator, we're going to have our original function. So that's that -1 to the n times x to the n plus 1 divided by n squared. And then we're going to go ahead and add 1 to all of those n's for the numerator. So we have -1 to the n plus 1. We have x to the n plus 2 this time, since it's already plus 1. And we have n plus 1 squared. So then we're going to go ahead and try our best to simplify this the best we can. The first thing I'm going to do is divide these two fractions from each other. So I have the limit as n approaches infinity of -1 to the n plus 1, x to the n plus 2, n plus 1, it's not an n, squared, times, and then we're going to flip the denominator, so I have n squared divided by -1 to the n, x to the n plus 1. Okay, now what I'm going to do is I'm going to rearrange it so that way the like things are together. So I have limit as n approaches infinity of the absolute value. So I'm going to put my -1 to a power, so the -1 to the n plus 1, and I'm going to divide that by -1 to the n. I have x to the n plus 2 and x to the n plus 1, so I'm going to put those together. And then we have n squared over n plus 1 squared. Okay, so now we want to simplify what we have. The -1's are going to cancel each other out, except for -1 to the first, but we're also absolute valuing it, so it is going to go away anyway. So even though it will remain negative, we're taking the absolute value so that goes away. X to the n plus 2 divided by x to the n plus 1. If I subtract n plus 2 minus n plus 1, we get x. And then we have n squared over n plus 1 squared, and that really doesn't simplify, so we're going to leave it as is. Things that we need to remind ourselves with limits is that if it's a constant number, then we can go ahead and pull it out front. And one of the things that we want to remember is that later on, when we plug in values for x, because x is not the variable that the limit is approaching, it is a constant number, because what we're really thinking about this as is we're plugging in a number for x and kind of doing a test. This is just a way to do that without having to test every single value. So we're going to go ahead and pull out this absolute value of x. It's not affected by our limit, so we can pull it out front, kind of like a constant, and still get an answer. Okay. Looking at this, I have the absolute value of x, so even when I plug in my limit, I'm going to have the absolute value of x. I'm going to apply our limit. We have a degree on top of 2, a degree on bottom of 2. They are the same, so we look at their coefficients. there's a 1 in front of n squared, there's a 1 in front of n to the first that is being squared, so we have 1 divided by 1, which is 1. So we have the absolute value of x by itself here, and we know that with the ratio test, we want the absolute value of x, whatever we get, to be less than 1. So some things that we know from this: the absolute value of x, the center is going to be 0 because it's x by itself. We also know that r is equal to 1 because that is the value that it is less than. So our interval right now looks like one in each direction. So added 1 from 0 is 1, subtract 1 from 0 is negative 1. What we don't know is what's going on at x equals negative 1 and x equals 1. So now we need to test our endpoints. So we need to test out when x is equal to 1 and when x is equal to negative 1. So when x is equal to 1, we have the summation from n equals 1 to infinity of an r function. We have negative 1 to the n times x. Well, x in this case is going to be 1 to the n plus 1 divided by n squared. So we're going to go ahead and simplify what we can. So we have 1 to a power, and no matter what I raise that to, it's still going to be 1, and when I multiply something by 1, it doesn't change it. So what this really is n equals 1 to infinity of negative 1 to the n divided by n squared. And what I can say is this is going to be an alternating series, so we want to do the alternating series test. So we have the limit as n approaches infinity of 1 over n squared. That's going to equal 0, which is what we want. And then we need a sub n is non-increasing, so a sub n is greater than or equal to a sub n plus 1. So 1 over n squared has to be greater than or equal to 1 over n plus 1 squared, and we can verify for sure that's true by multiplying both sides by the denominator. So n plus 1 squared is bigger than or equal to n squared for all n, so I know that this series is going to converge. And it converges by the alternating series test. The next thing that we might want to check is negative 1. So now we're going to go ahead and check to make sure that when x is equal to negative 1, what's going on. So we have the the summation from n equals 1 to infinity of negative 1 to the n times negative 1 to the n plus 1 divided by n squared. If I were to combine these together, so when we're multiplying two things of the same base, we add the exponents. So we get the summation from n equals 1 to infinity of negative 1. n plus 1 is going to be 2n plus 1 divided by n squared. We have if I were to plug in 1, we're going to have 2 times 1 plus 1, so we'd have 3. If I plug in 2, we're going to have 2 times 2 plus 1. So every single time I plug a value in, our function is going to spit out a negative number. So we don't even have an alternating series here. We just have -1 over n squared. So this would be like taking our values and multiplying them by a negative. This is a p-series. So we have a p-series where p is equal to 2. And we know that because p is greater than 1, so 2 is greater than 1, we know our series converges. So what we know is our interval of convergence is from -1 to 1. And we know that because we found our radius of 1 and its center at 0. And we also solved for each endpoint, so we know they both converge. So it's including both endpoints, so our radius of convergence is a closed interval from -1 to 1. You could also say -1 less than or equal to x less than or equal to 1. We need some sort of interval. So one of the things that you may notice is that it didn't ask for absolute or conditional convergence. It just asked for if it converged. So we don't need to check for absolute or conditional convergence. If it did, then we would check that. The big thing for absolute or conditional convergence are going to be questions like the one we saw first, where it's going to tell us something like it converges conditionally, and that's giving us a hint that it is an endpoint, or that it's diverging there, and that's going to give us that hint of what it really is.